Hello Internet, my name is Quinn and this is Blondihacks. So today we're going to start a fun new project. We're going to make a fly cutter. Now there's lots of established designs for these, but this is Blondihacks, so we're going to ignore all that and do something weird. What am I doing? I'm standing in my shop in the dark, pointing at a cell phone on a stick. Is this what my mom wanted for me? So you might be wondering what a fly cutter actually is. Well, it's typically something like this, and the idea is that it spins in the mill, and it's a single point cutter that allows you to surface large areas with very low tool pressure because it's a single point tool. So it's a bit like bringing a little bit of the lathe into your mill. And they are well known for producing some of the best surface finishes. So when you really need a perfect finish, a fly cutter is a good way to go. And they are just a fun thing to make. So this is the traditional design that you will see, and the main disadvantage to it is that it's unbalanced by its very nature. Because the main body of it is a wedge shape, the mass is unevenly distributed from one side of the cutter to the other, and so it's going to tend to wobble as it spins. Now, most designs for fly cutters just sort of ignore this fact and rely on the fact that the machine, the mill, is big and heavy enough to absorb that oscillation. But in principle, it does affect the surface finish of the cutter. So just for giggles, I'm going to take a shot at making a more balanced fly cutter. And the first step is going to be to make it a parallelogram shape rather than the traditional wedge. And that will balance the bulk of the mass from one side to the other. And then for the finer tuning, it's a little bit tricky because you've got the tool bit on one side, and one side is carved away to make room for the set screws that hold the tool bit in place. So to get all of that mass balanced, Fusion 360 is going to help us out here. So what I did is I took the body of the fly cutter, which is the only part that is going to have any imbalance in it, and I put a plane down the middle of it, and you can pretty easily just tell by looking at it where, what plane the balance is going to be different across. And so I cut the body in half on that plane, and then in Fusion I can select each part, and it'll tell me the mass of it because it knows everything is steel. So on one side we have half of the fly cutter body and then the weight of the tool bit as well. So the tool bit, as we can see here, is 4.538 ounces, and yeah, ounces are stupid units, but the units don't matter because we're just balancing one side with the other. And then the main body of the fly cutter on that side is 9.189 ounces, giving us a total of 13.727 ounces on the right side of the fly cutter. And then the other side of the cutter is 13.224 ounces. So we've got about half an ounce that we need to take out of the side with the tool bit on it. The scalloped area that's gives you access to the set screws is not enough to balance out the weight of the tool bit. So then I went back to the heavy side of the body, and in an area that wouldn't interfere with anything structurally, I just took another little scallop out, and I just kind of played with the numbers for the size of that scallop. Now, it's worth noting that this is just a static balancing that we're doing. With something that spins, it doesn't just matter that the weight is the same on either side of the balance point. It also matters where that weight is distributed relative to the axis of rotation. So what we've done here is basically what used to be called a bubble level for car wheels, where we've just balanced it and added weights on either side until it sits level. And of course, nowadays with car wheels, we do dynamic balancing, where you put the wheel in a machine that spins it at an approximation of road speed, and then the computer calculates based on the wobble of that wheel where to put weights and by how much. So with a dynamic balance, we could theoretically make this fly cutter perfect, but a static balance is going to get us most of the way there and should hopefully perform better than your average wedge-shaped fly cutter. Okay, to the junk pile for some material. I've got this big old slug of 3-inch 12L14 steel, which will make the body of the fly cutter. And in the other junk pile, we've got some 12L14 round bar that'll make a nice arbor for us. It's great when the stock that you need is perfectly centered in frame and in focus. And then over to the other junk pile for no reason other than I'd like to look at it. Okay, we're going to start with the arbor because the 3-jaw chuck is on the lathe right now and it won't be for long, so this will be an easy first couple of steps. So we're going to face the end off, as is a tradition on the lathe. And then with our old friend, the number 2 center drill, we're going to go in there and put a nice center in one end. And we're not going to use the center for a while, but it will become important later. And now we're going to part this guy off. So we're really just forming the blank that's going to become the arbor. And the arbor is actually going to be turned between centers. But for now, since we've got the 3-jaw chuck in the lathe, I'm taking advantage of it to do these easy operations. And Yahtzee. And then we flip this guy around and face off the other end. And this facing operation brings it to final length. And then we punch a center in the other end as well. Okay, so we're going to switch gears and start working on the body of the fly cutter using that 3-inch round bar. So over to the horizontal bandsaw to cut a slug of this guy off. And I'm leaving myself quite a bit of extra length here because we're working with some weird angles. We're going to be making a 10-degree parallelogram. So I'm always worried about not leaving myself enough stock when working with weird angles. So our stock is plenty long. And I thought I was being pretty clever. I had a bucket ready to catch this thing as it fell off of the saw, and I wasn't quite ready in time and it fell on the floor anyway. But it did make a really nice cut. You know, these cheap 4x6 bandsaws can actually do quite nice work if you tune them up a little bit. I'll link to a blog post that I did on tuning up these saws down in the description. Now back to the lathe, I want to use the 3-jaw to face the ends of that slug off, and to do that I'm going to need to use the outside jaws. So I'm removing the jaws from my 3-jaw chuck. If you're not familiar with how these guys work, on a scroll chuck, the teeth that are on the underside of the jaws that mesh with the scroll are of course directional, they're curved, and so you can't use the same jaws and just flip them around. You have to have 2 sets of jaws. So I'm removing these guys, making sure to note the order that they come out of and where they came out of. Especially with these inexpensive chucks, it's important to get the jaws back in the same slots and not just in the same order, because sometimes they reduce the runout in the chuck by grinding them after they're installed on the lathe. And then we grab the outside jaws and we feed them back in the reverse order. And you'll know you did it right if they all meet up in the center. Okay, give that guy a little test spin and it's running pretty well. Okay, and away we go, facing this guy off. And this is where the power crossfeed really pays for itself. I'm very glad that I spent the extra money to get a machine that had that. Spooky. All right, that's looking good. And I put a board down here because this is kind of a heavy part and I really don't want to drop it on my ways. So just in case when I pop the jaws loose, if it falls, it won't land on something expensive. And now we can flip this guy around and seat it on that machine surface and face off the far side. Facing off rusted surfaces is always extra satisfying. Look how clean we're making it. Now the next feature we're going to make is the hole that will take the arbor. And the arbor is going to be a 2 thou press fit, so this guy needs to be quite precise in dimension. So we're going to use the boring bar to do that. And we're going to be boring it deeper than is strictly necessary because, again, the top of that is going to be angled. And so far, our top and bottom faces are square to the sides and parallel. So we're just going to make the hole extra deep for now, and then we're going to face those angles later. Now we're going to use drills to hog out most of the material because boring is very slow and you have to make room for the boring bar. And so I'm going to start with a 1/4-inch drill, and I'll show you a little trick here to get a precise drill depth. So what I do is I push the drill up against the work and then I crank the quill in with the tailstock unlocked, and that pushes the body of the tailstock backwards. And you do that until it lines up with one of the major marks there, and then go back to the quill and set the 0 on the hand wheel. And so now you've got the front of the drill flush with the work, and then you've got a 0 on your hand wheel and a nice whole number on your quill markings. So now it's easy to count a precise depth. Now this isn't going to be perfect because the end of the drill is going to be seated into your center mark a little bit. So it might be off by 5 or 10 thou because of that. But generally speaking, this is an easy way to get a depth accurate with drills to within a few thousandths. Okay, so we go in with our 1/4 inch drill. And then I'm working my way up in a couple of sizes here. It's probably running a touch fast, but we'll press on. Then I go up to 1/2 inch, which is my largest normal drill. Now we're going for 750 thou here as our final dimension, so I want to go up one more drill if I can. So I'm going up one more size. This is a 47/64 drill that I happen to have, and it's a reduced shank drill. You got to be careful with these guys because a 1/2 inch drill chuck like this is designed for the torque that can be generated by a 1/2 inch drill. So when you put in a larger drill that has a reduced shank on it, you're adding more leverage to the end of that Jacob's chuck than it might be designed for. And so if you're not careful, this can happen. As you can see, the drill slipped a little bit in the Jacob's chuck there, so just be careful when you use reduced shank drills. Prepare for some drama because you are pressing the chuck a little bit beyond what it's designed for. Okay, now we'll use the face of the work to square up the tool post again and get ourselves ready for our boring operation. Now boring is kind of interesting because you have to touch off in 2 places. So I'm going to start with the end here. And once we're touched off, I can go down and set an indicator on my carriage to get my travel so we get our depth accurate. And then I can touch off on the inside and set our depth of cut, and away we go. Now I'm resisting making all sorts of terrible puns about boring actually being exciting here, so yeah, you're welcome. Now one interesting thing about boring is that because we made the initial hole with those drills, at the bottom of the hole there's going to be a 118-degree cone in there because that's the shape of the end of the drill, and we need to square up that cone. So as we get towards our final dimension on the diameter, then oftentimes you need to go in there and face the end of that hole off to get rid of that cone shape in the bottom. So that's what we're doing here. So I'm going into the center where the deepest part of that cone is, and then I'm winding out to face it off and square up the bottom of the hole. Now I'm intentionally leaving the hole a little shallow and a little small on diameter here because I want to be able to do a finishing pass on both dimensions at the same time. Similar to turning to a shoulder, you want to do that one pass where you go down and then face out. With boring, you'd want to do the same thing. So either you bore all the way in and then face to the center of the hole, or you start at the bottom of the hole, face out, and bore your way back out for final dimension in both directions. Okay, that's looking good. Now we're going to check where our depth is at, but this is actually an interesting problem because the hole that we're boring right now is not the final depth. It's a hole that's larger than what is actually needed because the hole is going to be into the surface of a parallelogram. So I thought I was being pretty clever here, and on the drawing I marked that 720 dimension, which is the depth of the hole if the angled section wasn't there, because that's what we're actually boring. However, as is often the case, I'm not nearly as clever as I think I am, and this is actually not quite correct. And I'll let you think about why that might be, and I'll tell you why here in a minute. But hey, past me doesn't know there's anything wrong yet, so checking our final dimension, we are 1.5 thou over 700. Okay, so we've got 18.5 thou to go on the depth, and we've got about 20 thou left on the diameter. So I'm going to do that in 2 passes, just to make sure I get a really nice finish. So I'm going to plunge into the middle of the hole, most of the way to my depth, and then I'm going to wind out facing off the bottom of the hole. I'm going to go out another 10 thou, and then I'm going to pull that bar back out. And then for my finishing passes on both surfaces, I'm going to push the bar back in to final dimension, and then I'm going to face inward across the bottom of the hole, achieving final dimension on my depth, and we'll end up with nice finishes on all surfaces. You can see here where that precise drill depth technique really helps out because we had just enough depth on the dimple at the center of the drill to get the boring bar started. If you can avoid plunging into the material with the boring bar, that really helps. Now the really critical dimension here is the diameter of this hole, because that's going to tell us the diameter that we need to make the arbor to get a precise 2 thou interference fit. So I got the snap gauge out here and I'm getting an accurate reading of this diameter. And then we measure this guy with the micrometer, and we came in at 749, which I'm actually pretty happy with, because then we can make the arbor 751 and get our 2 thou interference fit while still fitting the arbor in a 3/4 inch collet. And then on the depth, we actually came in at 723, so I won't win any awards for hitting that 720 dimension, but as you'll see shortly, this will turn out not to matter very much. All right, so now we're gonna need to do some facing over in the mill, and so we're gonna get the milling cutter in there after removing the collet that's actually already in there. And we're gonna set our big cylinder up here in the vise using the center of the vise as kind of a makeshift V-block. Now we're gonna flatten off the top of our cylinder. This will make more sense in a moment, but I'm gonna take 100 thou off in 2 passes. And then we're going to set that machine side down on some parallels. Tappy tap tap. And then we're going to machine another 100 thou flat on the other side. So now we have 2 flats on either side that we know are parallel. And what that's going to do is give us a way to hold this part in the vise in a repeatable way. And that's going to be really important for the next several operations. And now hopefully you can see why, even though the fly cutter is only 2.5 inches in diameter, I went with this 3-inch stock, because among other reasons, it gives us the room that we need to make these flat spots that we need to hold on to the part. So now we're going to set up to form the 10-degree parallelogram shape on our cylinder. So I'm going to use my angle blocks for that. And the nice thing about angle blocks is that they come in these foam cut cases, so that the blocks always stay. Oh, jeez, every time. All right, so the 10-degree angle block is going to set our angle, and then we use the flat sides of the cylinder that we made to grip the part. Tappy tap tap. And then we just mill this guy flat. And by milling it flat in this position, we're creating the 10-degree angled plane on the top that we need. So I start by milling crossways to just kind of knock that top corner off, but once we've gotten part of the way down, it becomes more efficient to mill on the x-axis, which is good because that's where my power feed is, so now we can get down to business. Now this surface finish isn't winning any awards. I think this cutter might be starting to get a little bit dull, but those awards are all political anyway. So I'm doing 40 thou passes here at 600 RPM, and the mill's working pretty hard. This is a big cutter, and so when it's engaged at full depth at 40 thou in steel, it's definitely working hard. And I would not say that this is fast. So I continued milling until that new plane that we're creating just met the 2 edges of the cylinder. All right, a quick cleanup, because vacuuming chips is super satisfying. And what passed me was thinking is that now, since I started with that 720 depth on this hole, I should now be able to measure the shallow side of the hole, and it should measure 434 as on the drawing. So what happened here? Well, let's go back to that drawing one more time. So this 720 here is what I thought was going to be the depth of this hole before the angle was cut. However, the assumption that is not obvious in this diagram is that the diameter of the finished part is 2.5 inches. However, my stock is 3 inches wide. So what that means is that this space right here on a 2.5 inch diameter part is a lot smaller than on a 3 inch diameter part. And so by milling that 10-degree plane all the way down to the edges of the 3-inch part, what I did is I made this space here a whole lot smaller and effectively cut into the final dimension of my hole. But not to worry, we can fix this. The advantage that we have is that we haven't yet milled the other side of our parallelogram. So the bottom of this part is still square to the hole. So all we need to do is go in here with a center cutting end mill, and I'm going to plunge down the extra depth that I need to get to my 434. And then I'm going to take it back over to the lathe, and I need to reverse the jaws on the 4 jaw like we did with the 3 jaw. But of course this isn't a scroll chuck, so you can just use the same jaws and flip them end for end. And then I indicate this in using the hole, because that's the only datum that we have on this part, the only point of reference. And I'm using an angled nose on my indicator so that I can get inside that hole. And I square my tool post once again. I'm using the face of the Jacob's chuck here because of course the part is now at a 10-degree angle, so I can't use that anymore. And here you can see the impression made by the end mill. And so all we have to do is feed the boring bar into that depression, touch off on the base of that new deeper hole, and then face our way back out. And you can tell by feel once we've reached the original diameter of the hole. If we go a little bit too far, that's okay. It'll actually just give a little clearance for the end of the arbor once we press it in there. So now I want to check the final depth of my hole to make sure that I've fixed the situation. But now there's an interesting new challenge because the bottom of this part is at a 10-degree angle. And so the depth micrometer is going to sit at an angle, and the anvil is going to go in at a 10-degree angle relative to the side of the hole. So there is going to be a little bit of cosine error in this measurement, but it shouldn't be enough to bother us. And we came in at 433.5, and I am going to take that. Okay, with our little oopsie fixed, it's back over to the mill now, and we're going to set up to face the other side of the body parallel so that we'll form the 10-degree parallelogram shape. So we go back down on the parallels and we clamp it down again, and we go to town with the shell mill once again and face this guy all the way down. So after all that, we've got our wacky parallelogram here, and my original plan was to just simply keep facing this down 2 dimension with my shell mill, but I think I need to pivot here because this guy is sitting at a little short of 1.4 and I need 1.2, so I've got 200 thou to come off of this, and my surface finish is starting to suffer here. It's degrading and the cutter is starting to squeak. So this guy is getting dull, and I don't think it's got enough in it for the other 200 thou. I also need this guy for a later operation, and frankly it's taking forever to remove this much material. A 2-inch cutter cutting full width on steel is a lot for my little mill, and 40 thou at a time. This is, and 2 passes per surface. This is taking a long ass time. And also not helping matters is I chipped a tooth on this cutter, so that's certainly not good for my surface finish. I was touching off on this guy, and I had the cutter stationary, and I thought it was above the material. It was actually slightly inside the material when I started the mill, and the sudden jerk of that caused this little corner to break off. So this guy's having a rough day. I do need to get a little more life out of it though, so I put a fresh hone on it just by hand with a stone, and it's nice and sharp, so hopefully I can get some more operations out of this guy yet. But I still have 200 thou to take off of here. So if I had a proper vertical bandsaw for metal cutting, that would be a great option. You could just rest this guy on here, maybe put a fence on it, and push that guy right through and take the bulk of that 200 thou off of there. I do not have such a bandsaw. I have my horizontal bandsaw, but that has to be clamped like this, and because of the parallelogram shape, it's difficult to clamp it well, and I don't know if my horizontal bandsaw, if I trust it enough to take off that small of an amount without drifting into the area that I need for my dimension. However, I do still have the 4-jaw chuck on the lathe, so I think I'm going to do this material removal here because I've got 2 nice parallel surfaces to work with, and I've got 2 flat sides that I can hold here in the 4-jaw. Now, the one weird thing about this setup is going to be that this jaw up here is gripping on an outward angle, so squeezing on this jaw is going to want to tend to push the piece out. But on the other end, we've got the opposite. We've got the angle working for us. This is going to clamp in very tight down here, and then I can tighten the crap out of these guys. So I'm going to have 3 very strong gripping jaws and 1 that's a little sketchy, but we'll see how this goes. Now I'm dialing it in as best I can, but it doesn't actually matter in principle because we're just facing, but getting it dialed in close to concentric will help reduce vibration from a big off-center mass swinging around. So I start by using the flat sides, and I can dial those in. You just wiggle it back and forth, and the highest reading that you see is when the flat side is vertical, and so you match those two readings on either side to get that axis dialed in. And then for the round parts, because it's a parallelogram shape, they're both at a 10-degree angle. So you can still kind of get a decent approximation as long as you use the same point on both surfaces because they're at the same angle. But it's not going to be perfect. So, again, I just got it as close as I could. And I tapped it in to make sure it was seated parallel on those jaws. And then I kind of eased the speed up gently just to make sure I wasn't going to end up with a 10-pound hockey puck in my forehead. And now we can get busy with the facing. So I'm starting with a light cut here just to kind of sanity check my setup. I don't want to stress it too much until I can trust it. And of course it's starting as an interrupted cut because if you remember from your high school geometry, we've got a cylinder at an angle that's been sliced, and that conic section is an ellipse. So we're basically facing off an ellipse. So it won't become a continuous cut until we are within the circle that fits entirely within that ellipse. And the setup turns out to actually be working quite well. So now I'm doing 40 thou passes. Now the one challenge I did have is you can hear here that I'm fighting with chatter a little bit. And it's wanting to chatter, again, because of that large oscillating mass that's swinging a little bit off center. And so it's setting the machine up for failure chatter-wise. Now one way you can keep an eye on vibration on the machine is actually just put a dial indicator on the carriage like this. And you can just kind of watch the needle. And from the motion of the needle, you can tell how much of a vibration is in the machine and by extension how close you are to chatter. But in the end, I have to say this worked out super, super well, and it was sure a heck of a lot faster than trying to face down 200 thou with a dull shell mill. And we ended up right on 1.2, so I will take that. Now this part is going to go back in the vise on the mill, so we need to deburr those edges. And I'm also stoning the flat sides because the jaws on the forejaw made a bit of a dimple there. I was clamping down on there quite a bit because I was pretty worried about that part coming out of that janky setup. Okay, so now we can set it back up in the mill and prepare for our next set of operations. But that is going to be all the time we have for today, so thank you very much for watching. Please do consider supporting me on Patreon. It is the patrons that keep this content going, so thank you very much to all of you who support me, and we will see you next time.